This presentation is delivered by the Stanford Center for Professional Development.
Okay, let's get started. So today we're going to the zoo. And this video segment, which comes from '93, this is from Nagoya University. It's quite interesting.
The moving style of gibbons shown in this video is called brachiation. The brachiation robot is a dynamically mobile robot modeled on the gibbon. It moves from branch to branch, swinging its body like them. The brachiation robot, which we have developed, has 2 arms and no body. The total length is 1 meter and the total weight is 4.8 kilograms. The arms and grippers are actuated with DC motors through harmonic drive gears. This is the movement without actuation. At first, the robot doesn't know how to move at all. Now the robot is going to learn how to locomote to the next bar. Motion planning of such a robot is a difficult problem because of its non-holonomy. Our robot is able to generate desirable motions by itself using our new heuristic method. The algorithm is based on trial and error of animals and human beings to obtain better motions. After the motion learning process, the robot can locomote from branch to branch, forward and backward. The posture of the robot is measured by gyroscopes built into the arms, and the joint angles are measured by encoders. The robot is calibrating its gripper position and closes it when it approaches the target bar. This motion is so-called the underhand motion. The robot can perform another motion called the overhand motion. This motion is naturally more difficult than the underhand motion because the robot has to stop the turning of the arm against the gravity force, and the movement is liable to become unstable. However, our robot also succeeded in performing continuous overhand locomotion. It needs more torque than the underhand motion, but this is more efficient motion with respect to time and energy consumption. When the robot fails to catch the target bar, it can recover by swinging with arms to obtain energy by a method based on parametric excitation. By continuously performing 2 motions, namely the motion to control the swing amplitude and the motion to approach the target, the robot can catch the target bar from any initial state.
Indeed. Well, this project continued, and probably we will see some more about it. All right. Let's get back to this. We're almost there. So today I'm going to cover a few examples. I know this is might be boring topic, but we really need to understand how we can do frame assignment, because this is the only way you can generate the forward kinematics. And what we're going to see is that once we have the DH parameters, essentially we will have the forward kinematics, which means we know the position and orientation. And a little later, in fact on Wednesday, we will see how this can help us finding the Jacobian. And later on we will see how can we find the dynamics. So these are very important parameters. Once you define these parameters, you define your robot kinematics. You need to add the masses and a few additional things, inertias, and then we have all the models. Okay, so you remember last time I discussed the attachment of frames, and we emphasized the fact that we have those axes of the joints that are going to play an important role, because those axes will provide us with, first of all, the information about the distance between axes, which is the common normals. So we identify these. You have one here, one here, one here. And when they are intersecting, basically that distance is 0, and that point is very important. Then we continue with finding all the origins, which are defined. Do you remember? How do we define the origins? Anyone? Hey. How do we define the origins for the first? So we take the intersection of the common normal with the previous axis, and that gives us this origin, etc. We said these joint axes will be aligned with the z-axis, so we are selecting our z-axis along those axes. So we have z1, z2, z3, z4, z5. Okay? And we said once we have those z-axis, we have the origin, now we take x to be along the common normal or perpendicular to the plane containing the successive z-axis. Okay? And that is, in this case, we're going to have those axes. And we also defined the different parameters, the 4 DH parameters, 2 distances and 2 angles. A, it's called what? The length of the links length. And this is the distance between the ZI axis. So AI is the distance between ZI and ZI plus 1 measured along the XI axis. Okay? Alpha I is the angle between these two z-axes, the same axis, zi and I plus 1, measure about xi in the right-hand direction. And the two other parameters are, one of them is variable, either the d, which measure distance between x-axes, so it's measuring the distance from the previous x to the current x, I, along the zi axis, and this could be a prismatic displacement or a constant offset. And the last one is, this is the most common thing that we're going to see, it's the joint angle, because most of those joints are revolute joints, and we're going to measure this angle about the zi axis between xi minus 1, the previous x, and the next x. So I'm going to take an example, and we're going to work out this example. And this is a typical example of the things that you have in your homework, in midterm, in finals. These are simple examples that we try to design so simple enough so you can solve them, and also interesting enough with the difficulties of assignment and everything in them. So you see this red frame, we are introducing, we are giving you a frame, we are calling it X5, Z5. This is a frame attached to the end effector. This is our task, and the goal is to find the transformation from the base to that frame. So we need to find the DH parameters up to this frame. And this frame is given to you here. It can be not given. We can ask you to assign it, but we are giving you the last frame. So also, I should notice, this is the typical way we describe the kinematics schematic kinematics of a robot. And I'm not sure if all of you are familiar with it, but what you see here is that you have an axis. This is the joint axis. This representation describes a revolute joint, the output of which defines the next axis. So this is coming at the output of joint 1. And the sliding joint here that slides like this is a prismatic joint. So we represent it this way. And the output is coming to define the link that leads to the next joint. So if I can get my cursor back. So this is the output. And here you have the next revolute joint. When we represent it this way, we mean that the axis is perpendicular to the plane. When we represent it here, we say the axis is in the plane. Okay? And the output is defining, what is this joint? Revolute joint. And the output of the revolute joint is connected to the end effector. Yeah?
Like plane?
So this prismatic joint actually is sliding along this axis. You see these 2 points? These are the sliders. So it moves. So it moves to the left and to the right.
You have a z-axis for the prismatic joint that is out of the plane. Is that differently?
So we have only here one joint that has an axis coming out of the plane, and this one is the revolute joint. You're asking me if we have the case of a prismatic joint that is coming out of the plane? Well, that might happen, and you will see the figure. There is a way of representing that. But when we do it, we usually use a sort of 3D representation to show you how it's coming out of the plane. So one thing, an important thing to remember is this is not a mechanism describing one configuration. You should try to imagine how this mechanism is moving. So you have to somehow capture the fact that if we rotate about the first axis, the end effector will move out of the plane. You see that? It rotates about the first axis. If it slides, so just move each axis and see the end effector motion. Can you see that? It slides. Now, if you rotate about the third joint, what is going to happen? We move in the plane if we were in that configuration. And when we move about the last joint, we go out of the plane about that axis. You see that? So you need really to imagine that motion, because if we go to analyze the workspace of the robot, you need to fill that workspace, and you need to find a way to imagine the three-dimensional motion of this mechanism and find the volume that is spanned by the motion of the end effector. Now, what we need to do is to do the frame assignment, and we are going to start by assigning origins and z-axis. And in this case, we have a lot of things that are already there. So you see the first joint axis, the second one. What particularity about those axes we have? So joint 1 and joint 2 are intersecting. So the intersection point is going to be an important point in this case. Joint 3 and joint 2, are they intersecting? So they are sort of what? The axes are exactly. I mean, they are sort of parallel. Basically, they are in two parallel planes. And the next one, the last joint, is intersecting with the revolute joint number 3. So we call this mechanism revolute, prismatic, revolute, revolute. And that's RPRR. Okay? Any questions here before we start? Good. All right, so let's start. And I'm going to start by putting the z-axis and the origins. So the z1 is along axis joint 1, z2 along z2, Z3 is coming out of the plane, Z4 is along that rotation, and there is basically no question. All of these are directly assigned, very simple. And we are introducing already a distance, and this is coming from, in fact, it will be clearly defined when we put the origins. So origin 1 is there, but could you explain why we are selecting origin 1 at that point, at the intersection of axis 1 and axis 2? Yes?
Does it minimize the number of variables that you've got? Well, they're all 0.
I was not asking about origin 0. If for origin 0, you're right. But for origin 1, this is imposed because you have the intersection of Z2 and Z1 at that point. This point becomes the origin of frame 1. So O1 is imposed, but we put O0, the origin of frame 0, at that location because we want to minimize the number of parameters. If we put O0 lower or higher, we will have a distance that we need to account for it in the parameters here. So for origin 3, I mean the next origin, O2, O2 comes to be here if we, and how did we assign it at this location? It is the common normal intersecting with axis Z2, we get O2. What about O3? Where is going to be?
At the second level. See.
So O3 will be somewhere here? 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 Okay. All right. Okay, so far so good. Now, O4. So how do we define O4? Is along the common normal between what did you say? Between? So when we define 3, we said it is the intersection of 3 with 4, right? For 4, it is 4 and 5. So because we define 5, we have the common normal between the two. How many common normals you have? Infinite. So we have a choice. We can put O4 in different location. We're going to select O4 there. And that will contribute to, as we will see, to minimizing the number of parameters. Okay? Now, let's introduce those parameters. So you are given this problem, but there are not enough. I mean, so what is A0? A0 is the distance between which axes? 0, 1, and they are coincident, so it's 0. Okay. Now, what about A1? So it is again distance between the z-axis, 1 and 2, 0. What about 2 and 3? That will give us A2. So there is some distance. So there are distances that are not written on the figure, and we are going to introduce them. So you introduce anytime those distances. So now we are going to need a parameter that describes the distance from O2 to O3. And that distance we just put an L, you call it L whatever, L2. We are going to need that distance, which is actually depending on the location of O5, and we are going to need this distance to O5, to axis 5, the distance between the x-axis. I'm sorry? Well, these you will see this will come to be associated with the following frames. That's why we are putting that indices. You're not going to use you're not going to have need for an L3. Okay, so when we start building the table, so we're going to need to assign the x-axis. I mean, so far I'm introducing those parameters without really assigning the axis and deciding what are the signs of those parameters. But what we need to do is to put the x-axis. So what is the first one? X1. Where is x1 going to be? So it will be x1 is perpendicular to, so it's perpendicular to the plane containing z1 and z2. So it could be in or out of this plane. We are selecting x1 out. If we select x1 in, that is fine, but that will change the sign of the angle between the x1 and the following x. So x2. x2 is, how do we define x2? It is along the common normal. And it points from O2 to O3, and that is x2. You see x2? Okay? A lot of fun. Now, x3. Where is x3? Z3, Z4, intersecting.
Same direction.
It could be the same direction as x3, or in the opposite direction. We are putting x3 in that direction, up. You agree? If you put it down, the angle will change when you measure it, and that accounts for it. And since then its relation to x4 will be accounted for, everything is fine. And x4, because we selected O4 there, x4 will go from O4 to the axis z5, so it will be down. Okay? So it is along the common normal from 4 to 5. All right. So now I'm going to show you the table, and you are going to see all the parameters. And I think you have them in your hands. So but I wanted to see if you can compute them without checking your table. Can you do that without looking? So don't look, and let's try to find a few of these parameters. So if we were to find the parameter alpha 2, so this is alpha 2. So what is alpha 2? Alpha 2 is an angle between axis 2 and 3, right? Measured about x2. So you go from 2 to 3. You see axis 2? You see axis 3? And you're measuring about x2. So what is the angle? 90 plus or minus? Minus, because you're going this way. Okay. All right, so I'm going to show you the table, and then let's check little more, just to make sure you. So was it minus alpha 2 is minus 90, so That is correct. In the configuration shown, in this configuration, could you give me what is the value of theta 1? What is theta 1? 0. That's correct. Why? Theta 1 is measuring an angle between the x-axis, between from x0 to x1 about the z-axis. And the two are coincident in this configuration. What is the variable in joint 2? What is the variable in joint 2? D2. So if I think about a variable q, q1, q2, so q1 is theta 1, q2 is d2, the variable. So what is the value of q2 in the configuration shown? It's about this. So I don't know how many inches. That is the configuration shown. Okay? So you just measure it, and that would be the configuration shown. What about theta 3? What is the value of theta 3 in the configuration shown? Theta 3 is measuring from x2 to x3 about z1. x2 is, you see x2 to x3? You see x2, it's up, and x3 is up. They are coincident. Okay. All right. So let's do something more.
Sorry, can you go back?
Yeah.
Wondering about D4.
D4.
Because as you've labeled origin 4.
Okay, D4 is the distance between x3 and x4. Where is x3 and x4? It's 0. So it's 0.
That's 5. You have D4.
Ah, so this here. How come this is not corrected? Where is it? Let's fix it. Thank you. Yes. There was a question? Yeah.
I had another question. In the reader, you said that a convention would be to pick your intersecting axis x to be so that the alpha was always positive. Is that, or did I misread that?
Well, I don't think you need to. I mean, you cannot maintain that. So I mean, there are so many different frames. You cannot keep your alpha. You pick it for the first one, and then it becomes negative in the next one. So I don't think this is possible. You cannot. You can never maintain the sign of the alpha.
Well, you said always from x I minus 1 to I would always be. So you propagate from.
Yeah. So I mean, as long as you have a choice and you can select it positive, then you do it, and that is fine. But if you put it negative, it is fine as well. I mean, it's overall. If you start with the minus, the way you assign your x in or out will change the sign. But any selection you make, in or out, will result in the same answer because the angles will account for that. There was a question here? Okay. All right. Okay. Well, I'm going to take a more realistic example, and this is a real robot. We will see this robot here later. This is the Stanford Scheinman arm. Vic Scheinman designed and built this robot. This is a 6 degree of freedom robot. It's among the few robots in the world that has a prismatic joint. So the third joint on this robot is translating. So when you pull here, you are moving along this axis, the axis of translation. So this is a prismatic joint. And it has this wrist that has 3 degrees of freedom, 3 intersecting axes. Actually, as you walk in and out, you can see a yellow arm in the museum exposition on the first floor, and you can see this arm over there. So what we're going to do, we're going to find the forward kinematics for this arm. And this is going to require us to go through the DH parameters first, but then we are going to compute these transformations associated with the DH parameters to find all the transformation for this robot. Then we multiply them out and find x, y, and z at the end effector, and find this orientation of the end effector giving the joint angles and the prismatic joint location. All right? We're ready? Yes? All right. So first, how can we do this? Well, we need a schematic. We need to see these joints, axes, and we need... So here is a schematic that we're going to use. It is sort of 3D. So in this case, the first joint... So always we are using the same concept. You have a rotation. The output is going to the next joint, a rotation. So let me explain. So the first rotation, the first rotation of the arm, this rotation about this axis here, and then this is connected to the second one. So I'm showing it this way. So this here is in the plane containing this axis, and this is orthogonal to it. So when we rotate about this axis, this whole structure rotates. Okay? And when we rotate about this axis, the following structure will rotate about this axis. Now, this whole structure translates in and out along this joint. The output of this joint is attached to the 3 joints, revolute joints, that are intersecting at this point and that form the wrist structure. So this is, in the wrist, you have the last joint, joint 6, joint 5, joint 4, and joint 3 is prismatic. Joint 1 and 2 are orthogonal, and joint 1 rotate the whole structure. Joint 2 rotate the structure following about this axis. So you have these 2 first intersecting axes. So do you see this mechanism now a little bit? Now, the last 3 joints are going to affect the orientation. So when we think about this, this is when we move the structure and the intersecting point is here. So this point is the intersection. This structure rotates about this axis. It rotates about this axis. This is joint 5. So joint 4 is like this. Joint 5 is along this axis, and joint 6 is along here. So if you put your hand here and rotate this, you rotate about the z-axis. If you pull it out, it will rotate about this axis. And if you extend it completely and rotate your joint 6, this joint 6 and joint 4 will become aligned. That is, this joint and this joint become aligned if you rotate this up and make this joint and this joint parallel. And this is a special configuration, a bad configuration. We call it kinematic singularity. Because when we move this joint up and the two are aligned, we cannot rotate anymore about this axis. We are locked. It's called wrist lock. So when joint 5 is equal to 0. Okay, so we're going to do the forward kinematics and place the first axis. You agree? Z1? Z2 going to be along second joint. Z3. I wonder why I put it there. Z4, Z5, and Z6. Okay, any question about the z-axis? So now we have our z-axis. These are the axes of the joint. Along the axis of the joint, we place these axes. And obviously, we place Z0 to be aligned with Z1 in that configuration. And that places the origin Z1, Z0 at the same origin. Z2, why the origin is there? With Z3. Okay. 4, 5. Oh, already. So this point is going to be the origin of three, 4, 5, and 6. All of them. Okay. Common normals perpendicular to 1, 2, x1. You see it? 1, 2, z1, z2, x1. 2 and 3, x2. Now, 3, 4, 5, and 6. So x2 is the common normal in the plane 2 and 3. Now 3 and 4 we yes.
Why is it x2 is downward, not upward?
We can put it upward. We can put it upward.
Okay, so it doesn't matter.
It doesn't matter. So if you put it upward or downward, all what that changes is the alpha angle and the theta angle and the following angles, and everything will be accounted for. So there is no problem. So x3 will be along z6, x4, and x5 is perpendicular to 5 and 6, so it will be selected this way. You can select it the other direction. And 6 is selected along the same direction of 5. So we are saying this is the position theta 6 equal to 0. Okay. Obviously, x0 is going to be selected here. If we select it in the opposite direction, it will introduce a theta that is different from 0. Here, the theta 1 is equal to 0. So we introduced distances. Now we need a distance between the x1 and x2 axes. This is d2. We need a distance between the origin of z2 and z3. And what else we need? I think that is what, that's it. We just need these two parameters. Okay. And here we have our definitions to assign and find the values. So this time I'm going to introduce these one by one. Yes?
What we understand here is that you don't have any information left about the distance between, for example, the wrist joint and the manipulator. So
the wrist joint and
the manipulator, like the end of the...
Oh, that last, so we didn't introduce the last frame here. Yeah, so there is no frame Z7. We did not introduce it, and this frame Z7 could be introduced later in any way without any problem. The point 04, 03, I mean that intersection point is part of the link, the last link. So it is just the first point on that link, and anything you select later would be fine because you are not introducing any variable. It's a constant transformation. This is what I said last time. Because the end effector is here, we can think about this point, but we might think about the end of the tool held by the end effector. So that frame is always changing. So most of the time, what we do is we compute the transformation to the wrist point, and then we do an additional transformation for the task. Okay, so we're going to do the first one, and we need alpha 0, A0, D1, and theta 1. So we can start like and just we fill it, or quickly. So what is alpha 0? Why? Alpha 0 is the angle between z-axis. Which ones? 0 to 1, and they are coincident. So 0. And what about A0? Because the intersecting. And what about D1? D1 is what? Distance between x-axis. 0. Anything left? Theta 1. So what is theta 1? Huh? Okay, good. Theta 1. And it is equal to, in this configuration? 0. Because x0 and x1 are coincident. So as we rotate, we are going to rotate x1 away from x0, and that will give us the variable. Okay. Number 2. Wait. Let's start from the other side. What is theta 2? It's variable. It's theta 2. What about D2? D2 measures the distance between what? Between what axes? X1 and X2. X1 and X2, you see D2. So it's D2. And what about, I shouldn't put D2, I should put L2 next time. Make it D2 equal L2. Yeah, I always didn't, I mean, I never liked the use of D2. Later on, I call it rho 2. So we are really not confused with D, the constant. But anyway, we call it D2. I'm not going to confuse you with that. D2. It could be a variable. Here it's a constant. What about A2? I mean A1. Why? A measure distance between A1 will measure 1 to 2. 1 and 2 are intersecting. Okay. So the variable was alpha. Why it's minus 90? What is this alpha 1? Alpha 1 is measuring the angle between 1 and 2, Z1 and Z2. You go from Z1 to Z2 about X1. So, right? This way. Minus 90. So if you put X1 on the, I don't remember whose question was that. If we put the X, you will just get a different angle. But now, on the following one, you are going to account for it. So you get positive for the first, but you pay for it later. Okay. Okay, 3 is, what is theta 2 for 3? I mean, what is theta 3 for the third joint? Theta 3, x2 to x3. So x3 is down, x2 is down. Measure about Z3. Z3 is this way. Anyone can tell me? What is theta 3 for joint 3? 0. Everyone sees it? 0?
Well, how come x2 is facing down, but from the transformations it looks like it should be facing the same way x1 is facing?
Okay, let's look at it.
Looks like they should.
You said x2? Okay. So x2 is facing down because it is perpendicular to the plane containing Z2 and Z3, right? So it could be up or down.
Do we need to say theta 2, I guess, plus 90?
Well, if you put it up, x2, if you put it up, the transformation between x1 and x2 will change, and then from 2 to 3 will change. But right now, with this selection, I mean, once you had a selection, you are accounting for it. So now x2 and x3 are parallel. The angle between them is 0. So theta 3 will be 0. What about D3? D3 is the distance between the x-axis. Right? X-axis. x3 to x. And what is this distance between x3 to x4 along the Z3? This is the displacement. This is the, you see, as you move, translate this prismatic joint, you are going to slide D3. D3 will increase. So it's the variable. So it is D3, the variable. And so 0, D3, A is the 0, A is between the Z axis, this is 0, and alpha is 90 degrees. So alpha 3 is measuring Z3 and Z4, and this is 90 degrees, about X4. Okay, now once you reach this location 3, actually you have the transformation to frame 3, which is at the intersection point of the wrist, and basically you have your position of the end effector. I mean the position at the intersection at the wrist point. And this position is not going to change anymore because all the other frames are going to have the same origin. So this distance between the origin here and here is going to remain the same later. What's going to change with the next joints is the orientation of this frame. How these joints move will affect the orientation of the end effector. So Z4 will have only one variable, theta 4, and Z5 will have a theta, an alpha 4 that is equal to minus 90 degrees. The alpha is the angle between Z5 and Z6. And the last one, 90 degrees with theta 5, theta 6. Okay? Yeah.
Why is it for I equals to 2, you have a D2 there? Shouldn't it be like L2 because it's a fixed?
I didn't hear.
Why is it for I equals 2, you have D2 under DI?
It's not a variable.
D2 is not variable. Well, yeah. I talked about it earlier. If you want, I can change it online. But so call it L2, please. I'm sorry. It's every year I have to change it and forget to do it. Maybe I can do it. Can I do it? Can you do it like? Wow, I can do it. All right. All right, that's better. That's better. All right, now we have the table. Whew. Well, you're going to do a few of these, and there will be always one more column, configuration shown. And you have to remember that you're looking at this configuration and you start to move it a little bit and look what is the value of the variable. Okay, so now that we have, oh, I have to change the next one. All right, later. Okay, so each of these, I'll do it now because I'm sure I will forget after. Well, let's do it this way. And save it. I'm sorry? Oh, yeah. Thank you. Okay, so now every row that you have here for 1, 2, 3, 4, 5, 6 is going to give you a transformation. You're going to use this information and you're going to have a transformation. So if we go here, we're going to find the transformation from, this is not 1, this is I. My God, what is happening to this? Someone didn't find all the mistakes. All right. So this is going from I to I minus 1. This is the transformation that you are going to compute as a function of your alpha, A, D, and theta. So you have these 4 parameters, and you are going to use them to compute these transformations. Okay? And as long as you are doing the assignment following this convention, you can apply this formula. So we're going to start. Here is the table, and we do the first transformation. You have 5 minutes. I'm kidding. So let's do the first transformation. And the first transformation is very simple. The only thing on the first row that is variable is theta 1. And you can find theta 1, cosine theta 1, minus sine theta 1, sine theta 1, and cosine theta 1. And then you have a 1 here. So this is what you obtain. The transformation from frame 1 to frame 0 is simply a rotation about the z-axis. Okay? And the origin is 0, the same origin. All right? Now, the next transformation is going to be from frame 2 to 1, not to 0. You have to be careful. So it will involve only one variable. And that transformation involves cosine 2 and sine 2. And because the origin is different, you see D2 appearing, which is now should be L2. Oh my God. Have to. This is going to be really tough if we keep going with this. I cannot even change it. All right. All right. What about 3 to 1? 3 to 2 is, so the transformation 3 to 2 involve only this variable, D3. There are no variables in the rotation. There are 90 degrees, which gives you cosine and sine of 0, and then basically you get constant. And the only transformation involved there is D3, the only variable. Okay? So we continue 4 to 3, 5 to 4, and 6 to 5. Okay. Have you written everything down? We have it? Okay. Now, how can we compute the forward kinematics? So we're going to multiply. That is, we're going to say the total transformation from frame n to frame 0 is we start from n minus 1 to 1, 1, 0, and we reach frame 0. Multiply them out. So here is 1 to 0. Here is 2 to 0. How did you obtain 2 to 0? Now, to do this multiplication, you can start from here. You can multiply n minus 1 by this, and you get one matrix. You multiply this, and there are many ways of doing this multiplication. But I'm going to just emphasize the fact that we are going to do it in a specific way, because later, the way we will do it, we will find intermediate computation that will help us find the Jacobian. So the Jacobian, actually, we will see that the Jacobian relies on this vector. That is the z vector of the rotation in frame 0. So we need the z vector in frame 0. In order to find the z vector in frame 0, we will start doing this multiplication by taking 1 to 0, 2 to 1 by 1 to 0. That gives us 2 to 0. And now I have the vector z2 in frame 0. This is z2 in frame 0. And this is z3 in frame 0. You see it? This vector? So this vector is going to play a very important role later. So we do the multiplication always this way. We take 1 to 0, 2 to 0, 3 to 0 by just multiplying one matrix by the previous one. So we start from the left and do the multiplication. Your question? Good. Okay, well, when I reach 3, 0, look what we have here. This represents the rotation of frame 3 with respect to frame 0. This is x3 in frame 0, y3 in frame 0, z3 in frame 0. And this is what? The origin of frame 3 in frame 0. Okay? Now, notice this is going to remain the same as we continue, because we selected the same origin, so the origin will not change. So 4 to 0, you see that last column is the same. So this last column here, cosine 1 d3 s2 minus s1 d2, well, if you go here, it is the same. It is the same, it is the same. But what is growing is, what is this? What is this? What this represents? Transformation 6 in 0. What is this? This is the end effector lost frame, frame 6. I have X, Y, and Z6. Z6 in frame 0 is so complicated. You have the sine, cosine of 1, cosine of 2, cosine of 4, sine of 5. All of this are the component, to compute the component of that lost vector Z6 in frame 0. This is its X component, Y component, and Z component. You see it? Now, these 3 columns are the rotation matrix from frame 6 to frame 0. Now, in this transformation, I have everything about this lost frame. We have the X-axis component in frame 0, the Y-axis component in frame 0, and the Z-axis component. I'm not showing you these two because there is no room. And the origin of frame 6 with respect to the origin of frame 0. So you have everything. So now you can form a set of parameters to describe your position and orientation. You can say I would select X, Y, Z to represent my end effector position. And then for the orientation, what are you going to select? Pick something. So what options we have? Do you remember? We had this in the first lecture, I think, or second lecture. We have angles, like 3 angles, quaternion, Euler angles, or direction cosines. What are the direction cosines? These. Just pick these. You have 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers that will give you your direction cosines representing essentially all the parameters in the rotation matrix involved with the orientation. So this is what we're going to do. Going to put the position xp, the coordinate of the position. I will use Cartesian coordinate x, y, and z, and that will be these 3. And now I'm going to use the 3 columns R1, R2, R3 to represent the rest. So this is big. This is big, and this is big. So what I'm showing you is the smallest part. So this is what? This is the Z6 axis in frame 0. This is the Y6 axis in frame 0. And this is X6 axis in frame 0. All right. So the forward kinematics, if we don't care about the orientation, is very simple. But if we care about the orientation, and we do care about the orientation, it is not very easy to capture. And now go ahead and find me the 3 angles associated with these. Right? How do we do that? Well, we go and say this matrix, rotation matrix, is identified to 3 rotations, and we compute the inverse of the cosine alpha. You remember beta, and then we make sure it's not 0, no singularity, and then we extract alpha and gamma. And all of that requires you to take those values, numerical values, once you plug it. Because what does it mean, C1? Cosine theta 1, right? So you measure theta 1 from your encoder, you get the value of that, and you have now cosine theta 1 and sine theta 2. So the orientation part is quite interesting, and that is going to be all the way interesting as we go to the Jacobian. In fact, this part, the z vector, is very, very important, because as we will see later, the Jacobian is going to be formed by just the z vector. Z1 in frame 0, Z2 in frame 0, Z4 to the end. That gives you half of the Jacobian matrix. And the other half of the Jacobian matrix turns out to be just simple differentiation of these three x, y, and z coordinates. So once we understood the forward kinematics in terms of the position and orientation, and then once we understood how, when we move the different joints, when we produce velocities at the joints, we affect the end effector velocity with linear and angular velocities, then we are going to be able to create this transformation between joint velocities to end effector velocities that uses the knowledge of the axis of rotation of different joints. This vector is important because about this vector that we have the velocity of the joint. The z-axis, you remember we selected rotation about the z-axis. So the theta 1 is measured about the z-axis, and that is going to play a very important role. Okay. Any questions? All right, well, I'll see you on Wednesday, and we will start working with the Jacobian.